Hi friends, this is Mr. Zarzak, and in this screencast I'm going to show you how we can derive equations of motions graphically. So let's get started. Alright, on the screen right now I have a velocity versus time graph. If I take a peek at the graph, I've included some numbers just for some talking points, okay, but the numbers are just kind of arbitrary. They're not really used in any context other than for us to be able to talk about some things along the way. This velocity plot, okay, you can see that the graph goes up and to the right. It's got a constant positive slope, okay, and so as time goes on, the velocity gets bigger. So, for example, at 1 second, there's a velocity of approximately 1 meter per second. At 2 seconds, the velocity has increased to approximately 2 meters per second, and so on and so forth. All right, and so what's happening here is velocity is just speed and direction. And so as time goes on, whatever this object is that's moving is getting faster. It's increasing its speed. I'm going to pick a couple points on the graph. Remember, we graph donuts in physics, so I'm going to put this point here. It's the first point that's on the graph, so I'm going to give it a name. I'm going to call this VI. All right, that I stands for initial. In fact, I think I'm going to put it over here. Yeah, like that, okay? And then at the end of the plot here, up at about 6 seconds, the velocity is about 6 meters per second. I'm going to call that VF. The F stands for final. Okay, so I have two values. All right, and so what I'm going to do is I'm going to take the average of those values. And since those values happen to be velocity, okay, that's going to allow me to compute the average velocity. So I take VI plus VF, and I divide by 2. Okay, just that by itself is pretty darn useful because I have another equation for average velocity. You just look at the change in the displacement divided by the change in time. Displacement, by the way, is distance with direction. Okay, it's how far you are from a reference point. All right, so I'm just going to label this. This is for average. All right, and let's give myself, let's make that a little less cluttered. There we go. Okay. That average velocity point, by the way, if I put that on the graph, okay, average or arithmetic mean really is just the midpoint, okay, and so that average velocity just appears right here. All right, as long as the line segment is linear, as long as there's a constant slope, okay, this little trick of using arithmetic mean or just like normal average formula works just fine. If the plot of the graph was a non-constant slope, so like if it looked like this, okay, or if it looked like this, or just any other kind of curve, okay, well then we wouldn't be able to apply just average, just take the average of the two numbers, add them up and divide by 2 would not work, okay? But the majority of the time in this class, we will be dealing with velocity graphs with values of slope that are constant, okay? If you want to deal with non-constant velocity slopes, that's an AP topic, and you'll need different mathematical tools for AP. Anyway, speaking of slope, okay, if we look at the slope of this velocity versus time graph, all right, well, in math class they teach us the general form for slope is the change in y over the change in x, or the rise over the run. Okay, well, in physics class we add the context of using proper variables, because if we do that, we can go deeper, we can get further interpretation. And so if I compute the slope of this graph, the change in the vertical variable, so we're looking at the change in velocity with respect to the change in time. And that right there, that is the definition of acceleration. Okay, acceleration means to speed up, slow down, or change direction. All three of those things fit within the context of acceleration, because acceleration is the change in velocity with respect to time, and velocity is speed and direction. All right, we don't really make the distinction of acceleration versus deceleration. We have speeding up and slowing down, but we just call those different varieties of acceleration. Accelerations in different directions. We'll come back to that idea in a little bit. Okay, so anyways, if I take this delta V or delta t, remember delta is a Greek for delta. It's just a letter in the Greek alphabet, and it signifies change, which mathematically means we need to take the difference. So I could take this and I could expand this out a little bit. So V final minus V initial. Okay, so just think like if we were doing this in math class, it would be like y2 minus y1. Okay, so our second value minus our first value, we're just giving them different subscripts, final and initial. Okay, we can do the same thing with the time as well. Oops. So we got final time minus initial time. Okay, our initial time is just 0, and our initial velocity is just 0. So both of these cancel out here. All right, and so really the time final is really just the time at any point in the graph that you're interested in analyzing. See, because let me clean this up a little bit. All right, we wind up with this acceleration is equal to VF. Okay, and I'm going to drop the F subscript on T for this context here, and you'll see why just in a second. All right, and then I'm going to take and multiply over the time to both sides to factor out this time. All right, and then I'm just going to take and rewrite this. I'm going to flip and put the final velocity on the left, okay, and on the right I've got t times a, which I can write as a times t, so it's from commutative property of multiplication. Okay, this VF, all right, this is what we call the instantaneous velocity. Okay, that's the how fast and which way is it going at some discrete point in time. All right, at some time, what is the velocity? That's what we say about instantaneous velocity. We've been dealing with average rates up until this point. Okay, well, now we've got a new tool in our tool belt. All right, at this point, I'm going to actually move to a second graph. Okay, we'll come back to that first graph in a second, or in a few minutes. And this is the case where the initial velocity does not equal to 0. Okay, and we can see here that if I labeled the initial velocity, okay, it looks like it's about 1 meter per second. Okay, so if I go through and I just kind of label the same points that I did here before, okay, so there's my VF. So the velocity at the end of the time segment, it's 6 seconds, but now the velocity is 7 meters per second, it looks like. Yeah, that's right. Okay, so it's a little faster than it was before, even though the slope of this graph is the same as the previous one, because I've got some non-zero initial velocity. All right, I can take and write the same two average formulas over here. So I'm just kind of doing comparing and contrasting. All right, so I can write average velocity is equal to VI plus VF over 2, so arithmetic mean still holds here because I've got a constant slope. All right, and I've also got average velocity, oops, it's just equal to the change in d over change in t. Okay, if I look at the slope of the graph here, okay, well, I'm still looking at the acceleration. That's an important point, all right? The slope of a velocity time graph tells us the acceleration. And so we have a constant positive slope, and so we have a constant positive acceleration. Let me make that, let's make that red, just to kind of match what we were doing before. Okay, so I got the delta V over the delta T. Okay, I'm going to take and expand this out in the same fashion, okay, that I did on the previous page. So V final minus V initial, T final minus T initial. Here we can't factor out the initial velocity because it's non-zero, but the initial time is, okay, and so just to simplify and eliminate a couple of subscripts, all right, we're going to take that out and just write this as acceleration is equal to V final minus V initial divided by time. All right, algebraic, same little trick where we're going to multiply by time to both sides of the equation to factor it out from the denominator over here. All right, and then I'm going to rewrite this. So commutative property of multiplication acceleration times time is equal to V final minus V initial. All right, and then I'm going to take and add this initial velocity over to the other side of the equation. All right, and I wind up with VI plus AT is equal to VF. And traditionally, okay, we take this and we just flip it around. We move the things on the left to the things on the right to get the general form of this. So final velocity is equal to initial velocity plus acceleration times time. And this right here, we need to circle this in, let's do black. Okay, this is the complete instantaneous velocity formula. Okay, this is a big one. We're going to use this one a lot. This is going to be one of our key equations, well, one for the entire year, okay, but primarily for the next 2 units. This is one of the 3 really big ones that we're going to need, so much so that I give it its own name. I call this one ultra mega 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 equation number 1. All right, so sneaking back up here, oh, and before I forget, the average velocity is still halfway up the hill. All right. Okay, so scooching back up here. All right, so one trick that we use when doing graphical analysis is we look at the slope and see if it tells us something. The slope of a velocity time graph tells us acceleration. We looked at the concept before. The slope of a position time graph tells us the velocity. All right. The other trick that we like to use is we look at the area underneath the graph. So similar to what we did in the PVA lab, I'm going to do that trick here as well. All right, and let's pick this kind of yellowy orange color. Okay. If I trace out the space underneath the graph, okay, I get a triangle. And I'm going to assume that we know that the equation for the area of a triangle is just half base times height. Okay, so then over here I'm going to do exactly that. All right, so the area equals 1/2 base times height, and that's just the general form of the geometry formula. Okay, just like the change in y over change in x is the general form of the slope formula. Okay, but I'm going to write this formula in terms of the variables that are actually on my graph. Okay, and so the base is just the time axis. All right, and the height is just the velocity axis. All right, so I'm going to rewrite this as area equals 1/2 times time times velocity, and I can get even more specific because, well, the height of this triangle takes us right to the final velocity. So I'm going to write that in terms of VF. All right, and now I'm going to take advantage of a little algebra trick, a little substitution, see, because, well, down here I have an expression that is in terms of VF. VF is equal to acceleration times time. And so what I'm going to do is I'm going to make a substitution. The area equals 1/2 times time. All right, and I'm going to take final velocity and replace that with acceleration times time. All right, you'll see what I'm doing here in just a second. All right, if I take this area, I get 1/2. Okay, I'm going to pull the a forward so that you can see that I have time times time, which is time squared. Okay, so I've rewritten the area formula for a triangle and I made a substitution to make it look a little different. Okay, and now what I'm going to do is I'm going to look at the units, okay, that are in the expression, because that's going to give me the hint as to what I'm really computing when I compute the area. All right, the units of acceleration are meters per second squared. That's like your standard units in the SI system or metric system. Okay, and then the units of time are seconds, but time gets squared, so the units get squared, so I wind up with seconds squared. And I'm multiplying these things together. There's a 1/2 coefficient in front, but I'm just looking at units now. Okay, and if I do this, well, the seconds squareds factor out, and I'm left with the units of the area, which in this case is meters. All right, because when you compute the area underneath of the velocity time graph, what you're really finding is displacement. All right, this simple relation is a way that we solve for displacement, or how far are you from where you started. That's pretty important. I think I'm going to write that down. Okay, the area underneath a velocity time graph tells us the displacement. All right. Now I'm going to take and I'm going to do the same basic trick down here where I'm already moving. I have a non-zero initial velocity so that I can get a more generalized version of this. All right, I am going to look at the area underneath the graph. Okay, so now to compute the area underneath the graph, okay, I can do one of two things. All right, the area under the graph, the shape that it takes on is this irregular trapezoid. Okay, and the way that you compute the area of this trapezoid is you take the average base, or the average height times the base. Well, the average height is really just the average velocity. and the base is the time. So average velocity times time is displacement. Hey, look at this. All right, that should look familiar. Okay, this is really just DRT. Rate times time is equal to distance. Rate of velocity times change in time is the change in displacement. Okay, so that's kind of neat, but that's kind of old hat. All right, so what I want to do instead is take and express the area in terms of two segments. All right, the triangle, just like we did before. Okay, and then the space underneath, all we have left is a little rectangle here. Okay, sorry for the overlap. All right, so for the top triangle, okay, I'm just going to use that little derivation that I did on the previous graph because it's still valid. All right, it's still just equivalent to this 1/2 AT squared. All right, the bottom rectangle, okay, well, I know that the area of a rectangle is just the base times the height, okay, and the area underneath the graph is displacement, so I'm going to write base times height for area of the rectangle just as, well, the displacement is the area of the rectangle, the base is the time, all right, and the height is just the velocity. Specifically, the height of the rectangle is this initial velocity. So if I take initial velocity times time, I've got the area of the rectangle. And if I take and I combine, or if I sum up the area of the top triangle and the bottom rectangle, I get the generalized form of the displacement equation. D equals VIT plus 1/2 AT squared. This is a big one. This one's really important. Okay, so important that I give it its name. I call this one ultra mega 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 equation number 2. These two equations right here, gigantic. Okay, I don't ask you to memorize things in physics, but I guarantee you before the end of the semester, you're going to have these memorized because you're just going to use them a lot because they're just so important. Okay, if I take and scroll on here, I've just got an example of a graph with 3 segments, okay, that spans 12 seconds, and we're going to compute the displacement in each segment, okay, because it's going to let us use a different part of ultra mega 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 equation number 2. All right, so this first segment here, okay, which goes from 0 to 4 seconds, okay, that's my interval. All right, the first thing I'm going to do is I'm going to compute the slope of the graph because I can. All right, so the idea that acceleration is the slope of a velocity time graph is a fairly new concept, so we can get some practice with it. Okay, so I got delta V over delta T, where that's the final minus the initial velocity, divided by the change in time, so T final minus T initial. All right, on the graph, I'm going to label my initial velocity here and my final velocity here. Okay, just reading the graph, my initial velocity is 0 and the final looks like it's 4 meters per second. All right, so I'm going to go ahead and compute the slope, which is the acceleration, just so you can see how we do this. 4 meters per second minus 0 meters per second. Okay, if you look at that time interval, okay, the interval ends at 4 seconds and it starts at 0. Okay, so really this is 4 over 4 and it's meters per second per second. So 4 over 4 reduces down to 1, and meters per second is written as meters per second squared. Okay, so this graph has an acceleration of 1 meter per second squared, so the motion is starting from rest, and it's move away at an increasing velocity with a constant acceleration. So you're speeding up at the same rate for the entire 4-second interval. Okay, and then I'm going to take and I'm going to compute how far. All right, now this comes from VIT plus 1/2 AT squared, all right, but the initial velocity of the graph can see here it's 0. All right, and so because of that, this part of the equation is going to factor out any number times 0. So any time times 0 is still just going to be 0. Okay, so I can simplify down. So d equals, oh, hey, how did that happen? D equals 1/2 at squared. All right, so for this 4-second interval, I got half times 1 meter per second squared times 4 seconds squared. Okay, and rather than go to my calculator, since these numbers are pretty easy to deal with, when I do this, I'll work backwards. So I'll take and I'll square 4 first. So 4 squared is 16. Then I'll multiply by 1 and divide by 2, and I've got my answer of 8 meters. Okay, in this first interval, okay, I wind up 8 meters away from where I started. All right. Now let's look at the green segment. Okay, so the green segment goes from 4 seconds to 8 seconds. All right. This is my final velocity for this segment. This is my initial velocity for this segment. If I were to compute the average velocity for this segment, I would add up the initial, the final, and divide by 2. So I'd be adding 4 plus 4 and then dividing by 4, which gets me right back to 4. See, so the average velocity, I could put it in the middle of the interval. But in this case, with a 0 slope, honestly, it doesn't matter where I put it because all these values are just equal to one another. All right. So the point is that there's really not much of a point in having any subscript at all because the velocity is constant. Okay. The initial velocity is the final velocity is the average velocity, and so were I to write out ultra mega 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 equation number 2 here, the displacement equation, well, if the slope of the graph is 0, the acceleration of the graph is 0. No acceleration. And so then this just simplifies down to displacement is equal to velocity times time. All right. The time interval goes from 4 to 8 seconds, so this time segment is 4 seconds long, during which I'm moving at a speed of 4 meters per second. So 4 meters per second for 4 more seconds means that I'm now 16 meters even farther. Okay, so in the green segment, I've gone an additional 16 meters to the 8 that I traveled in the first segment. And if you think about it, well, the area under the graph in that orange segment is a triangle, right? And what is a triangle? It's half of a rectangle. Okay, so it's really not so surprising that I've gone twice the distance because the base is the same in both. Each of them has a base of 4 seconds of length. Last segment, let's see, goes from 8 seconds to 12 seconds. All right. So just kind of for talking points, and so that we can apply ultra mega mega 2. There's my initial velocity, and here is my final velocity. So let's compute the slope. To compute the acceleration, delta v over delta t. All right. So v final minus v initial over t final minus t initial. By the way, as you become more comfortable with these notations, you don't need to necessarily write down both the delta version and the final minus initial version. Once you're comfortable, delta v over delta t is just fine. Okay, it's implied that that's going to be the final minus the initial. All right, one symbolic equation is enough. So here we got, let's see, what's the values? Final velocity is 6. Initial velocity is 4. Final time is 12 seconds. Initial time is 8 seconds. Okay, so I have 6 meters per second minus 4 meters per second. 12 seconds minus 8 seconds. All right, so 6 minus 4 is 2 divided by 12 minus 8 is 4, so 2 over 4. So I have half, or 0.5 meters per second squared. All right. If I look at this value, acceleration is 0.5 meters per second squared. All right, well, in the first segment of the graph, in the orange section, the acceleration was 1 meter per second squared. So what's the difference between these two? All right, well, there's more acceleration in the first part, yeah, but what does that mean? Well, in both segments, both the kind of bluish purple and then in the orange, okay, the velocity is increasing. Okay, so we're going faster, but the rate of increase in the orange section was greater than the rate of increase in this kind of blue-purple section. All right, think about it. when you're driving a car, right, the gas pedal is often called the accelerator. Now, a physicist would say a car has three accelerators: the gas pedal, the brake pedal, and the steering wheel, because those are all ways we can change velocity. But talking about the gas pedal, all right, you have options as to how hard you press the gas pedal. All right, you can push the gas pedal part of the way down and the car will speed up, but it's going to take you longer to get up to a certain speed if you only press the gas pedal halfway down versus if you floor it. Okay, that's going to give you a greater rate of change in speed. It's the same with the brake pedal. You can hit the brake pedal kind of gently and only push it part of the way down, and you will stop, but it's going to take you a longer period of time to do your stopping than if you slam on the brakes. It's still going to take you some time if you slam on the brakes, but not as long, because you'll have a higher magnitude of acceleration. All right. Anyways, once we have the acceleration, okay, then we can go and apply the displacement formula, ultra omega 2 VIT plus 1/2 AT squared. Okay, we're adding together rectangle plus triangle. All right, my initial velocity during the segment was 4 meters per second. All right, my time frame went from 8 to 12 seconds, so I got 4 seconds of time. All right, during this time period, not only was I moving, I sped up at a rate of 0.5 meters per second squared. And again, we're talking about this 4-second time interval. All right, so 4 times 4 is 16. All right, let's see, the other side, 4 squared is 16, times a half is 8, times a half is 4, so another 4 meters. Okay, add them together, so in this third interval, oh, how did that happen? T is equal to 20 meters. All right, so in this final segment, all right, I wanted an additional 20 meters. If I wanted to compute the total displacement, okay, I would just take my segments and add them up, so 8 meters plus 16 meters plus 20 meters. And that works out to, what is that, 24 plus 20, 44 meters. At the end of this segment, I am 44 meters away from where I started. Okay, each segment I achieved more displacement in a different way. All right, so that brings us to the end of this derivation and examples for these two velocity equations. This is Mr. Zarlik saying thanks for watching.